How are we doing, guys? We are looking at stationary points. That's if you're on text and test 5, it's page 110 to 112. We're going to look at these three questions here. Starting with 5 part 1. Find the coordinates of the following points of each of the following curves and determine the nature of each turning point. So it's for this curve here, there's a part 2 that we're going to ignore. So we know from meeting cubic functions before that as long as there's a positive coefficient for the cubic term, they'll look like this. It's negative, they look like that. And what we're being asked to find is the turning points. That's here and here. Okay, this one's called a local maximum, and this one's called a local minimum. Because you can see in its area, that's the highest point. In its area, that's the lowest point in the curve. There's lower points over here, but in the area around that point, this is the lowest point. Now, mathematically, how do we find that? Well, here's our function. And actually, straight away, you can probably see that the turning points there are at 2, minus 15, and minus 1. I think that's minus 112 up there. Okay, so we know the answer straight away. Here's what we're trying to show. That red line there is the slope of a tangent to this curve. Okay, so you can see there as I move this value a along at minus 2, you've got a tangent slope of 24. You can see over here. Okay, if I keep going at minus 1, you've got a slope of minus 1.86 over here in the function. But this is what I'm interested in, the turning point at x equals minus 1 exactly. Well, the slope of that tangent, that just becomes the line y equals 12. The slope of that tangent is 0. Okay, so that's your dy dx equals 0. Similarly, down here, okay, slope of the tangent at our lowest point is 0 as well, if I can get that to sit on 2. Okay, there it is there. Slope of the tangent is 0. So collectively, local maximum, local minimum, they're called turning points. And our condition is that at a turning point, dy dx, or the slope of the tangent line, will be 0. So we can come over here and say, well, what's dy dx? It's going to be 6x squared minus 6x minus 12, 0. We want to let that equal 0. We have a common factor of 6, so let's divide through. X squared minus x minus 2 equals 0. That factorizes as x and x, 1 and 2. We want a minus x, and minus 2 plus 1 equals 0. So either x is 2 or x is minus 1. Okay, and we saw that in our graph. Okay, x is 2 here, gives us one of our turning points, and x is minus 1 here, gives us the other turning point. We find our y values then by plugging these in to the function. So I know if I plug a 2 in here just from GeoGebra, I know I think I'm going to get minus 20 out. So y equals 2 times 2 cubed minus 2 times 2 cubed minus 3 times 2 squared minus 12 times 2 plus 5 ultimately gives minus 15. Sorry, I said minus 20 there. Minus 15. So that gives us one coordinate for our turning point of 2 minus 15, and that's this one. 2 minus 15. This one here, x equals minus 1 is earlier on. So that's x equals minus 1. So we can actually draw our axes in something like this. And that's minus 1. And what? Well, if we plug in minus 1 into this function up here, we're going to ultimately come out with 12. So that's minus 1. 12 is our local maximum. Now, it's reasonably obvious that our this point here is a local maximum, just from looking at the graph here. But we need to have a formal mathematical definition as well. So I want you to watch what the slope is doing. That red line has a very positive slope at the moment, 40.5. I know that's negative, but you'd have to move that over. Y equals plus 40.5. plus 86.25. But never mind the actual value, just look at it, it's positive. It's getting smaller and smaller and smaller, all the way up to 0, and then it keeps getting smaller and smaller and smaller. So around a local maximum, that slope, or that dy dx, is getting smaller. Okay, well, what are we talking about there? The rate at which the slope is changing, if it's getting smaller, it has a negative rate of change. But that's the slope, and we're now saying the rate at which that changes, that's the second derivative, d2y dx squared. In our case, 12x minus 6. Okay, the rate at which that's changing, when x is minus 1 at the local maximum point, this is going to have a value of minus 1. 12 times minus 1 minus 6 is minus 18. That's a negative value because the rate at which the slope is changing is negative. The slope of the tangent around this local maximum point is getting smaller and smaller and smaller. So here's our condition. At a local maximum, the second derivative will be negative, okay? The rate at which the slope is changing will be negative. Okay, and then the converse of that, well, as I keep going, as I move along here, look what's happening to my slope now. The slope of that red line is negative, but it's getting bigger, okay, or less negative. It's getting shallower and shallower until it gets here. Slope is 0, and then it keeps getting bigger, and now it's moving, it's got a positive value. Okay, so the slope of that line is getting bigger and bigger and bigger. The converse of what we've just seen is that at a local minimum, the rate of change of the slope, or the second derivative, d2y dx squared, is going to be positive. Okay, so if the second derivative is still 12x minus 6, but at x equals 2, if you plug in 2, you'll get 18 there. Positive value. At a local minimum, the second derivative is positive. Whoops. Greater than 0. Sorry about that. Now, some of you might have noticed as well that my slope here, okay, as I move left to right, it's getting smaller and 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 smaller to 0, and then smaller again, smaller and smaller. But somewhere around here, there's a point where it stops getting smaller and it starts getting bigger again. Okay, just around there at about x equals 0.2 or 0.3 maybe. Okay, that's called a point of inflection, and we're going to meet that in question 9 again. While I'm at it, I'll point out this blue curve here, which is called the slope function. Okay, and what that does is it tracks the slope of that red line at any given x coordinate. So at minus 2 there, okay, or minus 2.1, the slope here is minus 27. And if you come up on the blue curve there, you'll see there the slope at minus 2 is just up around here. It was minus 2.1. We're up at 27. Okay, that's our y coordinate. So what's interesting, at minus 1, the slope of our tangent is 0. So we've got the point minus 1, 0 is one of our coordinates. Maybe not too surprising. Minus 1, 0 is one of our coordinates. We've got 2, 0, okay, because when x coordinate is 2, the slope of our function again is 0. And you can see here on the left, this is a decreasing function. The slope function is decreasing. And on the right of this point here, okay, that's where our inflection point is. It's the lowest point in our slope function. And from there on, the slope function is increasing, which is what we saw as well from our point of inflection onwards. Watch that red line. From our point of inflection onwards, the slope starts getting bigger again, bigger and bigger and bigger. Right, we're actually going to go backwards here to question 1. Find the turning point of this quadratic function and show that it is a local minimum. Well, if you plot that out, you can see the turning point is at 2, 5, and it can only be a local minimum. That shouldn't be too surprising because we know that's a U-shaped function. So U-shaped functions only have a local minimum. But how do we find that point 2, 5 mathematically? Well, we say our condition is Slope of the tangent at that minimum point is 0. So dy dx equals 0. So what's dy dx? It's going to be 2x minus 4. That equals 0. 2x equals 4. X equals 2. Okay, there's our 2. How do we find the y? You plug it in here. You'll say y equals 2 squared minus 4 times 2 plus 9. You plug that 2 in and you get 4. Take away 8 plus 9 equals 5. Okay, so 2, 5. That's our turning point. How do we show that it is a local minimum? Our requirement, remember here, is that d2y dx squared needs to be positive at a local minimum. Well, dy dx, we found up here, was 2x minus 4. If you the second derivative, d2y dx squared, differentiate that, you just get 2, which is always positive because this type of function can only have a local minimum. So you don't have to plug in any x's or anything there. Okay. Okay, we're going to finish up question 9, part 1, by solving the equation d2y dx squared equals 0. Find the coordinates of the point of inflection. Remember, this is our condition for a point of inflection, is that the second derivative should be 0. Just to show you what that function looks like, x cubed plus 3x squared plus 1, there it is there. You can maybe spot that there's a point of inflection here at minus 1, 3. Okay, I'll run that slope as a slope of that tangent line gets smaller and smaller and smaller around your local maximum, keeps getting smaller until it meets that inflection point, and then the slope starts to grow. And you can see now that the slope is getting bigger and bigger and bigger at all points there. Okay, so this point here, minus 1, 3, how do we find that mathematically? Well, what we're saying is we need d2y dx squared equals 0. So what's dy dx first? That's going to be 3x squared plus 6x. That's our slope function, if you remember me using that phrase. The second derivative, d2y dx squared, is going to be 6x plus 6. And we need that to equal 0. So solving that, 6x has to equal minus 6, and x has to equal minus 1. Where on the function does x equal minus 1? Well, plug x equals minus 1 back in. Y is minus 1 cubed plus 3 times minus 1 squared plus 1. That's going to give us 3 times 1, 4, take away 1 is 3. So minus 1, 3 is our point of inflection. Now, if we come back and have a look at this slope function actually on GeoGebra, that's it there in blue. And just to point out that the slope function here, it's positive, positive, positive. So watch what the slope is doing again. Oh, sorry about that. The slope is positive, positive, positive. Right here, the slope is 0. So you're down here now on your slope function. And then the slope becomes negative, keeps getting smaller, becomes negative until it gets, the slope is at its lowest negative value down here at minus 3. So let's just scroll that along to x equals minus 1. Okay, just want to land on minus 1, that's okay. Here at our inflection point, we've got a slope of minus 3. You can tell that because that's our y coordinate on our slope function. And from that point on, our slope is growing the whole time. Slope of our tangent line, our red line, is getting bigger and bigger and bigger the whole time. And again, at this point, 0, our local minimum, it crosses, that's the roots of your slope function, cross here. You've got a slope of 0, and from then on, it's a positive slope. We're going to see more of that slope function stuff in the next exercise, so maybe don't worry about it too much. Can I ask you now to do page 110, questions 3 and 4, and question 9, part 2, please?